Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to use Hess's law to find the enthalpy of a given reaction. Let's get into this. So in this problem we're given methanol, a potential fuel source, can be prepared by heating carbon monoxide and hydrogen gas under pressure in the presence of a catalyst. And so here we're given the reaction equation and we want to find the enthalpy of this reaction. So they ask us determine the enthalpy change of this reaction using the delta H of negative 726.6 kilojoules per mole of the CH3OH, the methanol that is burned, excuse me, for the heat of the combustion of methanol and the following data. So they're giving us the following data. So we've got these equations. They're equations of formation of different compounds. So the heats that we're given here are the heats of formation of the various compounds from their elements in their standard states. So this is kind of the only time you're going to see fractions as coefficients in the equations because they're equations of formation. We're forming the products from, or the definition of the enthalpy of formation is that we're forming 1 mole of the product from elements in their standard states. So we need to only form 1 mole. So that's why we end up sometimes with fractions, because we need the fraction in order to only get 1 mole. So that's a little aside. Okay, so we're going to use Hess's law. Remember, Hess's law says that if you can add up a bunch of reactions that you know the enthalpies to in order to get the equation or reaction that you're getting, then you can add up the enthalpies of those reactions, and the result, the sum of those, will be the enthalpy of the target reaction that you're having, right? So let's get into this. So here, this is our target. So we want to get this equation from these equations, but we also need the enthalpy of combustion, the combustion of methanol. So we don't have the equation, we have to write that out. So remember, the combustion of your equation is going to be the CH3OH liquid plus oxygen, right? So we're gonna burn 1 methanol with oxygen. Oxygen, since this is a combustion reaction, we know oxygen has to be a reactant, right? And the assumption is always when we're burning or combusting a hydrocarbon in the presence of oxygen, we assume a complete combustion. And so the only products are going to be carbon dioxide and water. So CO2 gas plus H2O liquid. We're going to assume liquid here instead of gaseous vapor, since we got liquid water, and we're going to want water to cancel out. So just FYI. Okay, so now we've got one methanol and 1 oxygen molecule forming 1 carbon dioxide, 1 water. We need to balance this equation. So if we balance the equation, we start with carbon. So carbon, we have 1, okay. Okay, hydrogen's next, because remember, if you have an element by itself, leave that to last. And usually it's going to be oxygen, but not always. So hydrogen, we have 3 hydrogens on this side. We have 4 hydrogens on this side, and we have 2 on this side. So we need a coefficient of 2. And now for the oxygens, we have 1 oxygen here. We have 2 here. That's a 3 total. Here we have 2 oxygens. 2 times 1 is 2. We have 2 over here. So this is 4. So we need 4 on this side. So I have 1 here. If this was a 3, then I would have 4 total. So what times 2 is going to give me 3? 3 halves, or 1.5. So we're going to put 3 halves here. And so now this is balanced. And normally what we would do is we would get rid of the half and multiply everything by 2, so that way we have no fractions here. But the key you want to pay attention to this is they give us here, using the delta H of this combustion reaction of negative 726.6 kilojoules per 1 mole of methanol burned. Right now, our equation is 1 mole of methanol in the equation. So if we were gonna multiply this by 2, we would end up with 2 moles, and we would have to multiply this by 2 to get this equation. But we're going to end up, when we do our process here, we're going to end up dividing this equation by 2 anyway, so it doesn't really matter. You can multiply this by 2 and get rid of the fraction and then use that equation. But if you do that, you have to remember that they're giving you a negative 726.6 kilojoules per 1 mole. So if your equation has 2 moles in here, you're going to have to multiply this by 2 to get the delta H, right? So the delta H here for this reaction would have to be double that amount. But if I leave it this way, I only have 1 mole, it's still balanced, and I have a fraction there, right? It's still balanced. So I can use this and write this number down here, negative 726.6 kilojoules. And so that would be per 1 mole of the methanol that's burned. Since I only have 1 mole here, that fits. If I balance the equation and I say, okay, I want to get rid of the 2 here, I want to get rid of the fraction, then I can multiply everything by 2. But then remember, if you multiply this by a fraction of 2, you then have to multiply that by 2 as well. And again, it doesn't matter what you do or how you start this, because the math is going to work out anyway. Because you're going to end up having to divide this equation by 2. If you start with the 2 here in the methanol, and if you multiply everything by 2 and you start with the 2 methanol, at some point you're going to divide the equation by 2 anyway, and you're going to end up here anyway. But again, it doesn't matter. You should, as long as you do everything right, you should wind up with the same answer regardless. Okay, so I hope that wasn't too confusing. So here we go. So I've got my combustion reaction. I've got the enthalpy of combustion for this reaction. I want this. So I'm going to manipulate these equations in order to get them to add up to this equation. So the first thing I notice is I have here methanol liquid is a product, but here it's a reactant. So I'm going to have to flip this. So I'm going to have to get methanol, 1 methanol over here. So I'm going to rewrite this as CO2 gas plus 2 H2O liquid, and that's going to give me CH3OH liquid plus 3/2 O2 gas. And remember, according to the rules, if you flip or reverse the reaction, then you need to change the sign of the enthalpy. So this one was a negative 726.6 kilojoules. So if I flipped it, this is now going to be positive. So it's delta H is equal to positive 726.6 kilojoules. Okay, so I'm going to cross this out so I don't confuse myself. I'm done with that one. I flipped it. All right, so now I have that one. So I have the methanol on the product side. I have this methanol on the product side. I have only one, and I have only one there, so I'm good with the methanol. So what about hydrogen and carbon monoxide? Let's look at hydrogen. So here I have hydrogen, right? So I have hydrogen as a reactant, which is what I want, but notice I only have 1 hydrogen, but in my target equation I have 2. So I'm going to multiply this by 2. So I have to multiply the whole equation by 2. So this is going to be multiplied by 2 1/2 times 2 is 1, and then 1 times 2 is 2. And again, remember the rule is if I multiply my equation by a factor, I have to multiply the enthalpy of that reaction by the same factor. So this is going to be multiplied by 2. Okay, so now I have hydrogen on the same side, so that's good. Now notice I have carbon monoxide on this side here, but I want it on the reactant side. So this equation, I'm going to have to flip this equation. So I'm going to flip it down here. So I'm going to have CO gas going to graphite, made that a little long, C carbon graphite. That means you have carbon in the graphite form. You have the allotrope of carbon graphite. Remember, there's some allotropes of carbon. Carbon could be in the form of graphite. It could be form of diamond, right? So here we're specifying that graphite is the standard state of carbon in the solid form. So we have carbon graphite, and then 1/2 oxygen plus 1/2 O2 gas. And again, if you flip the reaction, you have to change the sign of the enthalpy. So now that's a positive. So this is going to be a positive. So the delta H here is going to be equal to positive 110.5 kilojoules of energy. So I'm gonna cross this out so I don't confuse myself. So that one's gone. I flipped it. It's down here now. And now notice I have graphite here. Now I have the CO. I have carbon monoxide 1, carbon monoxide 1. I have 2H2 gas here. I have 2H2 gas there as a reactant, and I have one methanol molecule here, and I have one methanol molecule liquid here. So I have all of the things that I'm targeting in the right place, but now I need to make sure everything cancels out that I don't want. And right away I see I have graphite here, but I don't have any graphite in my equation, so I need to cancel this out. So I'm going to need to use this equation here. So the graphite here, I have one graphite on the reactant side, I have one graphite on the product side, so that's going to cancel out. So I'm going to keep this just the way it is. So now I want to make sure everything cancels out, and so I already said, okay, one graphite on the reactant side is going to cancel out with one graphite on the product side. Excellent. Okay, now here I have 2 water liquid. I don't have any water here, so I need water liquid to cancel out. I have 2 water liquid on the reactant side. I have 2 liquid water on the product side, so that's going to cancel out. So that's gone. What else? Oxygen or carbon dioxide. Let's do carbon dioxide. That's probably easier. So here I have carbon dioxide as a reactant. Do I have carbon dioxide as a product? I do right here. So carbon dioxide as a product on this side, going to cancel out with carbon dioxide as a reactant on this side. Now for the oxygen. Notice here I have 2 oxygens, right? So I have 2 oxygen molecules on this side. Do I have any other oxygens? No. So I have 2 oxygen molecules on this side. So I need I need 2 oxygen molecules on the product side. So I have 3 halves here of oxygen, and I have 1/2 here. So 1/2 plus 3 halves gives me 4 halves, which is 2. So the half here of oxygen, the 3 halves are going to cancel out with these 2 here. And I think that's it. So let me circle what I have left. I have 2H2 gas left. I have CO gas left. And I have the methanol left. And that is going to add up. Those are going to add up to CO gas plus 2H2 gas is going to give me CH3OH liquid. So, ladies and gentlemen, I have my target equation right here by adding these together. So, now let me put stars by the ones that I added together just to make it clear. So this one I added together. The ones that are crossed out are gone. I already manipulated those. So this one I added together, this one, and this one. So these four equations added up equal this one. According to Hess's law, since I added these equations together to give me this one, I can add the enthalpies together to get the enthalpy that they want here. So the delta H of this reaction is going to be equal to all four of those added together. And when I add those together, I get a negative 128.0 kilojoules of energy. And that, ladies and gentlemen, is how you use Hess's law to help you figure out the enthalpy change of a reaction that's given to you when you're given a bunch of other reactions to work with. And that, ladies and gentlemen, is the end of the video, and I hope you enjoyed the video. I hope this helped you out a lot. If it did, then by all means, like the video, share the video, hit the like button over here somewhere. Also, do me a favor, subscribe to my channel, hit that notification bell. When you do, click all. That way, when I put out a video, you'll see it. You'll see all of them. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me, and have a great day.